Alright guys, so today we'll be talking about Riemann sums and definite integrals, which actually come from Riemann sums if you use an infinite amount of triangles. Okay, Riemann sums we talked about last time as being the sum of all of the areas of the triangles underneath a curve. Okay, and that those parts of the triangles actually touch the curve, and we can actually approximate. So this is actually an approximation. Okay. Well, I'm so... let me fix that. Approx. There we go. Okay, so that's an approximation. Okay, now it basically consists of two parts: the height of the triangle times the width. And the width can actually be found by taking b minus a, okay, which this would be b, and this would be a, okay, and dividing by n. And n is the number of triangles you want, or the number of rectangles you want. Okay, so it's something as simple as that. Now, to actually find the height of the triangle, you need to actually plug in the values when you get there. So let's say in this case, let's say we want, let me see, we got 4 triangles, 1 to 2, 2 to 3, 3 to 4. Let's say we want n equals 3. Okay, so if n equals 3, we're going to find out the width to be, let me see, 4 minus 1 divided by 3, which is just going to be 1 each. Okay, now when I'm dealing with this right here, when I'm working with these triangles, so I'm going to go to 2, and I'm also going to go to 3. Okay, and this is going to be a left-handed limit, alright, just for the sake of this problem. I'm sorry, not a left-handed limit, a left-hand Riemann approximation. Okay, so we're going to use these actual values at 1, 2, and 3 to actually get the actual measurements and everything. Okay, and so what you do is you just do several different things. So the actual area is going to be equal to 1, which is the width of the first rectangle, times, and this curve is x to the third, so I'm going to plug in 1, so that is 1 cubed. Okay, and then I'm going to add the next triangle, which is going to be 1 times 2 cubed. And then I'm going to add the next rectangle. And if I keep saying triangle, I apologize, you guys, but I'm just making mistakes with my rectangles and triangles. Okay, alright, and so this is basically 1 plus 8 plus 27, which actually gives us a length of 36 units. Okay, so this underneath this curve, and now let me just point out, this is an approximation under this part. We aren't counting this part, we aren't counting this part, we are just counting this part. Okay, so when you do the Riemann sums, you're just doing an approximation. Now, if you did want to find the difference between the Riemann sums and the integrals, or the error, you would just take the Riemann sum and divide it by the error, and you would see how close approximately you are getting. Okay, but if you treat, I remember my math professor in college saying, if you treat calculus as a really intricate way of doing a whole bunch of shapes with geometry, if you treat this as geometry, it's going to make your job a whole lot easier when you use it. Okay? Right, now we're going to take a look at this problem, but we're going to do it from an integral. Oh, I'm sorry. Before we go on to the actual measurements and everything, please understand we're going to use these numbers a little bit differently over on the next slide, okay? Alright, so when we do a definite integral, we're going to take our function, which in this case f of x is going to be x cubed. Oops, I'm going to put an equal sign between them. That would make more sense. Okay, we're still doing the same thing, except we're doing it with an infinite amount of triangles, or rectangles. Okay, the width is d of x. D of x is actually delta x of infinitely small widths. Okay, So that's delta x. And then f of x is just going to be simply our function. Okay, now the cool thing is that when we do this, it's just going to be capital F of 4. Well, no, in this case, yeah, from 1 to 4. Yeah, we're going to actually use the endpoints, not the left hand or the right hand or the midpoint of them. Okay, minus the function, the antiderivative plugged in 1. So you have to remember that f of x is going to equal the antiderivative of f of x. Okay? Alright, and if you look at your antiderivative rules, if our original function is x to the third, okay, then it's going to be 1 over n times x to the parentheses n plus 1 power. Okay, so in this case it'll be 1 over, well, it's going to be n plus 1. Jeez, what am I doing? N plus 1. So it's going to be 1 over 4 times x to the 4th, or you could just say x to the 4th over 4. You know, it's totally up to you how you want to do it. Okay, so what we do is now we know that that is going to be, this is going to be f of x right here. Okay. Alright, so what we are going to do is we're going to actually calculate it. Okay, now some of you guys are probably asking, like, why do we subtract? What is the point of that? Well, if you did f of 4, here, let me use a different color. If you did f of 4, okay, if you found the integral under the curve, you would actually be finding the area of the whole thing. But if you remember, we're starting at 1. So I'm over counting this part, which would be the integral of the portion over here, the area over here. So if I find the whole area and then subtract this little part, I'll get this portion. So you have to remember your geometry rules, especially your composite figures, in which you have weird figures, but if you cut out certain areas, you'll get this weird figure area, but it's like one big area minus a small area for like a donut type object. We don't know the formula for donut, but we know the formula should be the big circle minus the little circle. Okay. Alright, so in this case, our big circle is f of, the antiderivative at 4, so it's going to be x to the 4th, so that is 4 to the 4th is 256 over 4. Some of you guys will be tempted to just go ahead and simplify that, but please resist temptation. Okay, and then we're going to minus 1 to the 4th, because 1 to the 4th power is going to be 1. Okay, so this actually turns into a nice little number, 255 over 4. Okay, and that is the actual area. And if you wanted to compare that with the Riemann left, you do have to connotate whether it's a Riemann left or a Riemann right or a Riemann mid. So you just take the two and just calculate it that way. So if we go back to our actual area, the actual area is 36. So it's 36 divided by 255 divided by 4. And if we check out on our calculator, 36 divided by 255 divided by 4, well, we'll find that that's actually half of the area. So the Riemann left approximation is not the best. Okay, so it's 56%. So that actually got about, we were about a little over half right, but once again, it's approximation. It gives us a rough idea. Okay, and if you check out what 255 divided by 4 is, it's about 63.75. Okay. All right. So that's how you work with Riemann sums and definite integrals. And if you're wondering how to do these two right here, this is Alt 244 and this is Alt 245. This is Alt 30. Let me see if I have to go back here. Oh, sum. I just did a bigger version of sum. Sigma. Sigma is Alt 228. Okay. All right. So good luck, you guys, and have fun.